Welcome to today's lecture. Myself, Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. The subject that I am covering in my lecture series is microprocessor. Subject code is KCS 403. Today I will be discussing the peripheral devices, that is 8237 DMA controller. So what is DMA? The DMA input-output technique provides direct access to the memory. So if the peripheral device wants to access the memory directly without the intervention of CPU, then this scheme is used. So what will happen? The peripheral device will ask the CPU to relinquish the buses, because the peripheral devices obviously needs the buses to perform the operations. So it will ask the CPU to hold on and allow all the buses to be used by the peripheral device directly to access the memory. So during the DMA operation, CPU can be involved in those activities where the buses are not needed. So this is possible. But yes, the CPU cannot perform those operations where the buses have to be involved, because buses at that time are being used for the DMA operation. So this technique provides direct access to the memory while the microprocessor is temporarily disabled. Like disk memory systems and video systems, these are certain examples which uses the DMA operations. So like disk memory includes floppy, fixed and optical disk storage. Video systems include digital and analog monitors. Now the two control signals which are very important for the DMA operation and which are related to the microprocessor are hold pin and HLDA pin. So these two signals, these two pins are always available on every microprocessor which allow the DMA operations. So hold pin is the request pin. The request comes from the peripheral through this pin, and the request is to relinquish the buses. And the HLDA pin is an output pin from the microprocessor, and which is an acknowledgement pin in response to the DMA request. So what is actually happening, that the hold signal is sampled in any clocking cycle. When the microprocessor recognizes the hold, it stops executing the software and enters the hold cycles. So this we have to note, that hold pin has higher priority, even higher than INTR and NMI. So hold pin is having the higher priority even from the non-maskable interrupt. The only microprocessor pin that has the higher priority than the hold is the reset. So only the reset is the pin which is having the higher priority than hold. Otherwise, hold is even having the higher priority than the non-maskable interrupt. So in this way, during the rising edge of the clock, this hold signal is sampled here. So now another clock cycle, the next clock cycle, HLDA signal is issued in response to the arriving DMA request. So direct memory access normally occurs between an input-output device and memory without the use of microprocessor. So DMA read transfers the data from the memory to the input-output device, and DMA write transfers the data from input-output device to the memory. So in this way, these read and write operations are performed during the DMA operation. The memory and input-output devices are controlled simultaneously, which is why the system contains separate memory and input-output control signals. So this is somewhat beneficial in this transfer scheme. The DMA reads causes the DMA, that is the memory read control signal and input-output write control signal to activate simultaneously. Similarly, for the DMA write allows that the memory write and input-output read control signals to both activate. There are different transfer modes in case of DMA. The single transfer mode is, it transfers one data value for each DMA request assertion. So this mode is the slowest, because whenever the request is asserted and it is approved, it is acknowledged, then only one transfer takes place, one data transfer takes place. So for another data transfer, another arbitration has to be done. So this arbitration is not a major problem on the lightly loaded bus, but when there is the when there is a high load on the buses, then, or we can say when the multiple devices are connected and they are asking for the bus issue, then it leads to the latency problems. So in that case, block and demand transfer modes increase the system throughput by allowing the DMA controller to perform multiple DMA transfers when the DMA controller has gained the bus. So in the block and demand transfer modes, whenever the bus control has been obtained by the peripheral device, then the bulk transfer, or we can say the large amount of data is being transferred in these modes. So let's see what are these modes. For the block mode transfers, the DMA controller performs the entire DMA sequence as specified by the transfer count register at the fastest possible rate in response to the single DMA request from the input output device. So whenever there is a single request, in response to that request, the block is transferred. So during the demand transfer mode, for the demand mode, the DMA controller performs the DMA transfers at the fastest possible rate as long as the input output device asserts its DMA request. So as long as the request arrives on the DMA controller, then that long the transfer of the data will take place. So this is dependent upon the DMA, the demand of the bus. So this is how a DMA controller will look like. So the DMA controller provides memory with its address and controller signal DAC, selects the input output device during its transfer. So the DAC is the that is the DMA acknowledgement is the signal, which is an acknowledgement signal whose direction is from the controller, DMA controller, towards the peripheral device. So in this way, these are the control signals which have been generated. These are the write and HLDA and memory input output signals. So this is how the connections, the control signals are being generated. The 8237 is not a discrete component in modern microprocessor based systems. It appears within many system controller chipsets. It's a 4-channel device. So 8237 is a, so this diagram was just representing how the control signals are activated during the DMA operation. Now we are going into details of DMA. So 8237 is a 4-channel device, that is the simultaneously 4 peripheral devices can send the request at the same time. So it is expandable to any number of DMA channel inputs by cascading the devices. So 8237 is capable of DMA transfers at the rate of 1.6 megabytes per second. Each channel is capable of addressing a full 64 KB section of memory and transfers up to 64 KBs with a single programming. So this is the interrupt 8237 interrupt controller pin, that is a 40-pin IC, and the various signals being presented here have the different functionalities. So let's understand these signals. DRQ 0 to 3. These are the 4 individual channel DMA request pins. Through these, the DMA request arrives from the peripheral devices to the microcontroller, from the peripheral devices to the DMA controller. So these are the input pins to the DMA controller and which are used by peripheral devices for request. When the fixed priority mode is selected, then DRQ 0 has the highest priority and DRQ 3 has the lowest priority. Now DAC is the acknowledgement signals, that is the output signals from the DMA controllers towards the peripheral devices. These are the active low DMA acknowledge lines which updates the requesting peripheral about the status of their request by CPU. So these lines can also act as the strobe lines for the requesting device. These D0 to D7 are the bidirectional data lines which are used to interface the system bus with the internal data bus of DMA controller. In the slave mode, it carries the command words to 8237 and status word from 8237. So these are some important words. I'll show you what are these. In the master mode, these lines are used to send the higher byte of the generated address to the latch. This address is further latched using the address strobe signal. Input output read. This is an active low bidirectional tri-state input line which is used by the CPU to read the internal registers in the slave mode. In the master mode, it is used to read the data from the peripheral devices during a memory write cycle. Now again input output write, it's an again active low bidirectional tri-state line which is used to load the contents of the data bus to the 8-bit mode register or upper or lower byte of 16-bit DMA address register. This is again possible, or the terminal count register. So these are the possible contents which can be carried by this input output write signal, that which is the that it will indicate, it will be used to load these very contents. In the master mode, it is used to load the data to the peripheral devices during the DMA read cycle. So input output write control signal indicates the loading of these data. Now clock, it's a clock frequency signal which is required for the internal operation of 8237. Reset, it's used to reset the DMA controller by disabling all the DMA channels. A0 to A3, these are the 4 least significant address lines. In the slave mode, they act as the input which selects one of the registers to be written or read. In the master mode, they are the 4 least significant memory addresses, output lines generated by 8237. Chip select is an active low chip select line. In the slave mode, it enables the read-write operations to or from the 8257. In the master mode, it disables the read-write operations to or from the 8237. A4 to A7, this is the higher nibble of the lower byte address generated by the DMA in master mode. Ready, it's an active high asynchronous input signal which makes the DMA ready by inserting the wait states. HRQ, that is, it's used to receive the hold request, that is a hold. This is the input pin to the microprocessor from the DMA controller. So it is used to receive the hold request from the controller. In the slave mode, it is connected with the DRQ pin input line. In the master mode, it is connected with the hold input of the CPU. HLDA, it's a hold acknowledgement signal which is being sent from the microprocessor to the controller. MEMR, it is the low memory read signal which is used to read the data from the addressed memory locations during DMA read cycles. Again, MEMW, it's a write active low write operation controller signal, that is it 3 state signals which is used to write the data to the addressed memory location during DMA write operation. Address strobe is used to convert the higher order byte of the memory address generated by DMA into the latches. AEN, that is the address enable, it's used to disable the address data or address bus or data bus. Terminal count, it stands for terminal count which indicates the present DMA cycle to present the peripheral devices. So it indicates the end of the transfer. The mark will be activated after every 128 cycles or integral multiples of it being from the beginning. It indicates the current DMA cycle is the 128th cycle since the previous mark output to the selected peripheral device. So indicates the current. So this signal gets activated after every 128 cycles of the DMA operation. VCC is the power signal. So this is how all the modules of the DMA controller looks like. So these are the various channels, the 4 channels of the DMA controller, and for every channel there is DRQ signal and DAC signal. In this way, there is the read-write control logic, data bus buffer, control logic, and the mode select logic block is here having the ready, HRQ, HLDA, MEMR, MEMW, AEN, and address strobe. These signals are the part of control logic and mode set register along with the terminal count and mark signals. So this is how whatever I have explained, that how the hold request is sent and then it is acknowledged. This is what is represented by this figure using the switches. So this I have already explained how the hold request is sent from the peripheral to the DMA controller, and then the DMA controller holds that request further to the microprocessor and it is acknowledged in return. So, and after that the buses are relinquished from by the microprocessor and they are used to perform the DMA operation. So these are certain internal registers used in the DMA operation. The current address register, it's a 16-bit memory address used for the DMA transfer. Each channel has its own current address register for this purpose. When a byte of data is transferred during DMA operation, the current address register is either incremented or decremented, because with every transfer of the data, this address has to be increased or decreased depending upon how it is programmed. Now, the current word count register, it counts the number of the words which have been transferred. So, it's used as the counter. Now, this is the command register. It performs the operation of the DMA controller. It uses the bit position 0 to select the memory to memory DMA transfer mode. Like this bit position 0 represents its memory bit transfer disabled or enabled. Then again, bit number 1 represents the channel 0 address hold has been disabled or enabled. Similarly, bit number 2 is for controller is enabled or disabled. Now, next bit represents the normal timing or the compressed timing, where the very next represents fixed parity or rotating priority. So, all these things are representing that how the controller has been programmed. So, like next bit represents late write selection or extended write selection. Next, the DRQ sense is active high or active low. Similarly, DEC sense active high or active low logic pins. So, this is how these are programmed. Next is the base address and the base word count register. These are used when auto initialization is selected for a channel. So, what is happening in auto initialization mode, that these registers are used to reload these very registers which I have already discussed, that is the current address registers and the current word count registers. So, automatically these registers are loaded into the base register and the base word count after the DMA operation is completed. So, what is happening, that the current address and the current word count registers are automatically reloaded with these registers in the auto initialization mode. This is defining the modes, various modes. This is known as the mode register. That is, in channel 0 is selected, or 1 or 2 or 3, which of the channels among the 4 have been selected. So, in which mode the DMA is working, that is in the verify the transfer, whether it is writing or the read transfer, or it's an illegal combination. Similarly, auto initialization is disabled or enabled, and address increment is enabled or disabled. Similarly, there are the various modes, as I have already discussed, that demand mode, single mode, block mode and cascade. So, which of these modes have been configured. So, in this way, this mode register is used to select these modes. Again, this is the status register, and these 4 bits are indicating whether the terminal count has been reached for each of these channels, and this indicates that whether the DMA request pin is pending on these channels or not. So, this is the status register. That's all for the DMA operation. So, DMA controller, we see that it's used to establish a connection between the peripheral device and the memory directly without the intervention of CPU. So, that's all for DMA. Thank you.